Hello friends, this video on isolation of elements part 8 is brought to you by examfear.com. No more fear from exam. Now let's see some application of the thermodynamics principle of metallurgy. There are three applications which we'll study in this chapter. The first one is the extraction of iron from its oxides. The next one is extraction of copper from its cuprous oxides. And the third is extraction of zinc from its oxides. Let's talk about the first one, that is extraction of iron from its oxide. See, we know that iron is generally, the ore of iron is generally in the oxide form, right? So this is the common ore we have. We have ore in the form of FeO, Fe2O3 and Fe3O4. These are the common ores for iron, right? So these oxides of irons are mixed with limestone and coke. So this, we see here, this is a blast furnace. We'll talk about the blast furnace. So in this blast furnace we have this oxides of iron, and also we mix here limestone and also coke, right? Limestone is what? Limestone is my CaCO3 and coke is my carbon. So I have iron oxides, calcium carbonate and carbon. All these three are mixed and it is fed into the blast furnace from the top. This is the blast furnace, this is the top of the blast furnace, and this is the bottom of the blast furnace. Correct. And blast furnace, if you see, the typical height of this blast furnace is almost I can say 20 to 35 meter. This is 20 to 35 meter. It's very tall actually. And the width of this blast furnace is almost 6 to 14 meter. So if you see, the blast furnace is like this. It is somewhere in the middle. The width is more, and again it shrinks, right? So it is of this shape, this kind of shape. Okay. This is a little tall structure and it is a little wide in the center, not on the center exactly, but in the middle somewhere it's wide, and again it shrinks. And it can withstand temperature up to 2300 or 2400 Kelvin. That kind of temperature it can withstand, right? And it was first created by Abraham Darby in 1709. Abraham Darby is the guy who created this. So if you let's understand what we do in this blast furnace. The good part about the blast furnace is there is a difference in temperature. If you see, this level has a temperature of 1000 Kelvin. This side has a temperature of almost 2000 Kelvin. So this is a low temperature zone. Again, 1000 temperature is not a small low temperature, but again comparatively I'll say lower temperature zone, and this is a higher temperature zone. And from these sides, hot air is pumped in, and that's why you have more temperature here. If you see, hot air is pumped in from both these sides, correct? And that's why if you see this side, this area has higher temperature. So if you want to see what happens, if you see here, iron oxides and calcium carbonate, that is limestone and coke, is fed from the top. It goes down and somewhere it gets dissolved, right, in this area. And from the left and right, hot air is pumped in, and what you get output is a carbon dioxide gas. Carbon dioxide gas is actually waste, so that goes to the atmosphere. And this is the typical working of blast furnace. Here the blue one is my iron oxide plus calcium carbonate and coke. All these three are mixed and they are dumped from the top. And if you see, the iron, the pig iron is collected. The blue one is the pig iron, and the waste is slag. It is collected on the right hand side. The slag is lighter than pig iron, so it floats. Actually, this is all liquid. Actually, this is all liquid because at this temperature, iron, pig iron, slag, everything is in the liquid form. So since the slag is, we'll talk about slag in detail now. Slag is lighter. It floats and the pig iron is little heavy, so it is in this area, and thus we collect the pig iron here, and at the little higher place we have this hole, and from this hole we get the slag. This is a typical working of the blast furnace. So now let's see the reactions involved, right? So in this blast furnace, typically the iron oxide is reduced to iron metal. So the main reaction I'll say is you have iron oxide, you have this coke here. So coke will reduce iron oxide to iron. Let's see the reactions involved. See, in this case, I am putting iron ore. Iron ore can be my Fe2O3, can be my Fe3O4 also, right? So let's see the reactions involved. So at this lower temperature zone, the reactions that take place is at this lower temperature zone, my Fe2O3 reacts with carbon monoxide to give Fe3O4 and carbon dioxide. This carbon dioxide goes off. We also have Fe3O4 also, and also Fe3O4 is one of the products. So Fe3O4 again reacts with carbon monoxide to give iron and again carbon dioxide. This carbon dioxide also goes off. And also Fe2O3 reacts with carbon monoxide to form FeO sometimes and CO2. This carbon dioxide also goes off. These three reactions take place at this range, the lower temperature range, that is almost 1000 Kelvin, that kind of range, right? So it takes place in the range of I'll say 500 to 900 Kelvin kind of range. We'll see in this graph why this reaction is taking place. Now at this higher temperature range, this one higher temperature range, we have some more reactions. So at this higher temperature range we have reaction FeO, which we get here, plus CO gives Fe plus CO2. Fe is my pig iron. Also I have used the coke. Coke will react with oxygen to form CO2 and heat. It will form a heat. So this heat is also increasing the temperature here. It's not only the hot air from here which is increasing the temperature here, but the source of heat in this area is C plus O2 gives CO2 plus heat. Again, if you see, carbon again reacts with carbon dioxide also to form CO, and again heat is emitted. These two reactions actually provides heat in this area, and in this area a lot of FeO is there in this ore also, and from this reaction also. This FeO forms iron in this range. End of the day, whatever iron we have formed, right, if you see this Fe3O4 form is utilized in this reaction, and FeO formed in this reaction is utilized in this reaction, right? So typically the end product is only, if you see, carbon dioxide and iron. Carbon dioxide goes off and carbon monoxide again will be used somewhere else in the reaction, right? So Fe is, since it is heavy, it settles down, and carbon dioxide, since it is lighter, it goes off. Now this is the case where we have impurities also in case of iron ore. In the iron ore we have some impurity also. For impurity only we have used this limestone, right, to form slag, because the impurity, the typical impurity which we find in the iron ore is SiO2. So we have to take care of SiO2. How to take care? So for that we can, in fact we use this one, limestone. So we use this reaction, calcium carbonate is the limestone, it forms CaO plus SiO2, and this CaO plus CO2, and this calcium oxide will react with my SiO2, that is my impurity, to form a slag, CaSiO3, and this is the slag, CaSiO3, and this slag is lighter than iron. So actually this slag floats over this pig iron, and this slag is collected here, and pig iron is collected here. So that is a typical reaction we have, right? So iron plus limestone. The reason why we are adding limestone is because in this iron ore we have SiO2 as impurity, and we want to remove it off. And coke is used for reduction and also to create heat in this zone. So this is a blast furnace, and it has different temperature. The upper part of the blast furnace is the lower temperature. The lower part of the blast furnace is a higher temperature. This high temperature is because of the hot air plus this reaction. Carbon plus oxygen gives carbon dioxide plus heat, and also carbon plus carbon dioxide gives carbon monoxide and heat. Because of these two reactions, you have a lot of heat here. Now, if you see here, we are applying the thermodynamics principle. Why? Because if you see, these two reactions happen at two different temperatures. Right? If you talk about FeO and carbon monoxide reaction, if you see from this reaction, this Ellingham diagram, so this is my FeO line, right? And this is my carbon to carbon monoxide line. So if you see, these two lines meet at a temperature of this, right? That means anything above this is required to reduce the FeO, iron oxide, and we use a higher temperature. Okay, so this is what happens. Once again, I have my iron oxide, limestone and coke dumped from the top, and these reactions happen. Calcium oxide, the limestone is added because we wanted to remove this SiO2 as the impurities. It forms slag, CaSiO3 with this reaction, and different temperature is used, and different temperature in different zone, different reaction take place. These reactions, the top three reactions, take place at the little lower temperature, that is almost 500 to 900 Kelvin, and this reaction takes place at a higher temperature. Now we'll talk about the extraction of copper. Before we go to the extraction of copper, let's understand the kind of iron we get here. So as I told, this is a slag, and the iron which we get from this blast furnace is called pig iron. This pig iron is an impure iron which has almost 4% carbon, and it has many impurities also in small amount. For example, it has impurities, this pig iron, let me write here, this is 4% carbon plus impurities, and these impurities are my sulfur, phosphorus, silicon, etc. And this is called pig iron, right? And this actually you can cast into different shape, this pig iron. Now, little better quality from pig iron you get is cast iron. Cast iron has 3% carbon. It has lesser impurities, but again this is also hard and brittle. This is also hard and brittle. And if you want to make it a little better, we get wrought iron. Wrought iron. This is the purest form of carbon. It has 0.1% carbon. And this is the purest form of iron actually. This is the purest form of iron, and this is prepared commercially by from this cast iron we prepared this by oxidizing the impurities in a furnace, right? And the furnace is lined with hematite. See, the reason why we are using hematite is we have to remove this carbon, right? So the typical reaction is, this is my hematite Fe2O3. When this react with carbon, what you get is iron and carbon monoxide. Carbon monoxide is a gas, it goes off. If you want to write a balanced reaction, yeah. So with this, the percentage of carbon we are removing. So this is extra iron. So in this furnace, what happens is there is a furnace, let's suppose, and this furnace has a lining of Fe2O3. This Fe2O3 actually eats up all the carbon. Correct? Because we have a wrought iron, we have a cast iron that is nothing but Fe, but it has carbon also. We have to remove this carbon concentration. To do that, what we do is we use a blast furnace, or we call it reverberatory furnace, and this reverberatory furnace is lined with Fe2O3. Fe2O3 is nothing but hematite. This is lined with hematite, correct? And now when you heat this hematite, which is in this zone, will eat away this carbon, will take away this carbon by this reaction. This hematite will react this carbon which is there in this cast iron, which is there 3%, it will react with this carbon to form carbon monoxide, and carbon monoxide will go up. With this, the percentage of carbon will go down. And if it is 0.1%, we call that wrought iron. And if you see a good example, the whole Eiffel Tower, the big Eiffel Tower, is constructed using this wrought iron. This is purest form of iron, you can say. It is commercially used to make bridges, houses, everywhere we use this wrought iron. Correct? So it's a very important process. Understand, see, cast iron and pig iron are not of much use because they're very hard and brittle, because they have a huge concentration of carbon. So in pig iron we have a huge concentration of carbon plus impurity also. So what we do is we oxidize and we remove the impurity, right? We remove the impurity to get cast iron. The impurity is less, but still the carbon content is more. Then again we oxidize in this reverberatory furnace using Fe2O3 to reduce the carbon concentration. Once the carbon concentration is 0.1% or below and impurities are not there, then I call that iron as wrought iron. Now let's discuss about the extraction of copper from oxide. Now if you see extraction of copper, if you see this copper reaction, this is my copper reaction, and the typical reducing agent is we use this carbon plus oxygen gives carbon monoxide. If you talk about this reaction, so if you see these intersect at this point, that means after this point, after this temperature, carbon should be able to reduce Cu2O to copper, and that's a very low temperature. If you see here, almost at 200 plus, right? This is 200 degrees Celsius. Yeah, so 200 degrees Celsius plus temperature, right? Carbon will be in a position to reduce my copper oxide to copper. Pretty easy. But the catch here is copper ore is not in oxide. Naturally occurring copper ore are found in the sulfide form, right? Copper generally occur in the sulfide form. So what we do is copper occur in the sulfide form, we'll convert this into oxide first, because oxide to copper is pretty easy, correct? Sulfide form to oxide form, and then we'll get copper pretty easily by heating it with coke in a very okay type of temperature, almost 300 to 400 degrees Celsius kind of temperature, right? So to convert the sulfide to oxide, we need to roast it. So during roasting, copper sulfide is converted into copper oxide, and the reaction is this: you have sulfide, you convert this into oxide form, right? And the real reaction is I have Cu2S is a copper sulfide, you react with oxygen and you heat it. In the presence of oxygen, you get copper oxide and sulfur dioxide gas. You can balance this reaction. Once I have got the copper oxide, I can reduce it to form copper. Cu2O, I can reduce in the presence of carbon to form copper and carbon monoxide. Now, if you see, typically this copper ore will have an impurity, right? This have an impurity, and this impurity is iron oxide. This is the impurity in the copper ores. We have seen in iron oxide, in iron ores, the impurity was silicon oxide, right? But in this case of copper, the impurity is iron oxide, and you have to remove it. Again, we'll form the slag, and in this case, to form slag, we'll add silica. We'll add silica to form slag to remove my impurity, and in this case the impurity is FeO. So the reaction will be my FeO, that is my impurity, and SiO2 I have added to form FeSiO3. Please remember, in the last slide we have seen that in case of iron ore the impurity was silica. So we used to add calcium carbonate, that is limestone. So in this case the impurity is FeO, so we add SiO2, that is silica, to form this iron silicate, and that is a slag. So in the furnace, this slag, that is iron silicate, and the copper both will be produced, and we can remove the slag because this will be lighter. Okay. So if you want to see all the reactions, let's see all the reactions that happens in this extraction of copper. So the reactions are like this. I have FeS. I'll first write the impurities here. FeS. It reacts with oxygen to form FeO and SO2. SO2 goes off. So this is again my impurity. And this FeO which I have got will react with my silica to form FeSiO3, and that is my slag. If we talk about the copper part, I have explained this. Copper sulfide, when you roast in the presence of oxygen, you get copper oxide and sulfur dioxide gas. This copper oxide can now be reduced, right? You can either react this with Cu2S to form copper and SO2, or you can actually use carbon also. And please note, in this case, solidified copper, whatever is obtained in with this process, if you see, is called blistered copper. Why it is called blistered copper? Because when the copper is formed, sulfur dioxide gas is also formed. Because of the evolution of sulfur dioxide, this copper which is formed gets small holes, because from those holes actually sulfur dioxide gas comes, right? Because of those holes, this copper is called blistered copper. The next is extraction of zinc from the oxide. See, for the extraction of zinc from oxide, we'll use this reaction. Actually, if you see this reaction, club with carbon plus oxygen is carbon monoxide. This reaction, if you see these two reactions, these two lines merge at this point. That means any temperature beyond this point, that is any temperature beyond 800 degrees Celsius, is in that temperature, carbon will be able to reduce zinc oxide to zinc. So zinc oxide, we have this carbon, it will form zinc and carbon monoxide, and temperature will be almost 800 Kelvin, sorry, 800 degrees Celsius. Correct. So the question says the reaction Cr2O3 plus aluminum gives Al2O3 and Cr. For this delta G is minus 421, and this value is at the room temperature. But still the reaction doesn't happen. Why? If delta G is negative, the reaction should happen. So for this, we know that there is something called activation energy. So we have seen this kind of graph, right? So typically this is reactant and this is product. So typically we have seen that even there is a difference in the energy between reactant and the product is in the lesser side, and delta G is negative, but sometimes you need some energy to activate this kind of reaction, and that is called activation energy. Right? So even if the reaction is thermodynamically feasible at a room temperature or at a given temperature, the reaction doesn't happen because some extra energy, activation energy, is required to initiate the reaction. So the question is it true that under certain condition Mg can reduce Al2O3 and Al2O3 can reduce Mg? Yes, correct. If you see this line for aluminum oxidation, this is for Mg oxidation. Right? So in this case, if you see these reactions, they merge at this point. So anything on the left hand side at this temperature, my Mg and this temperature is almost 1350 degrees Celsius. So any temperature below 1350 degrees Celsius, you will see magnesium will be able to reduce aluminum oxide, Al2O3. Any temperature above 1350, if you see, this is line for Mg and this is line for Al. So aluminum will be able to reduce magnesium oxide, right? See, the way it works is the line which is in the lower, right? So in this case, aluminum will be able to reduce magnesium oxide. In this case, magnesium is in the lower side, so magnesium will be able to reduce aluminum oxide, correct? And if you see this, since they are intersecting, so the point is 1350 degrees Celsius. So below 1350 degrees Celsius, magnesium will be in a position to reduce aluminum oxide. Temperature above 1350 degrees Celsius, aluminum will be in a position to reduce magnesium oxide. And this detail we are getting from Ellingham diagram. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.